Anybody have any thermo questions? So last time I introduced the first law of thermodynamics. And that says that the change in energy of your system is equal to the heat minus the work. And remember, really, this is conservation of energy. The negative on the W is just because of the sign convention. A positive value of W means that our system is doing work on the surroundings. So that's where the negative comes from. And remember that E is equal to the kinetic energy plus the potential energy. Let me do next. So this is the kinetic energy. This is the potential energy. And this is the internal energy. This has to do with just molecular motion. And often, the change in kinetic energy and the change in potential energy are going to be small, and we're going to ignore them. Okay. One type of work that we're going to see all the time is the work of expansion. So if your system expands, it does work on the surroundings. Think of almost all the time, everything that we're doing, we can think about as happening in a piston and a cylinder. What? Huh? Okay, one common type of work is the work of expansion. Deja vu. So if you think of a piston in a cylinder, this is the gas that's our system. If that gas expands, that piston rises, and that does work on the surroundings. If the surroundings push that piston down, then that compresses the gas. That does work on the system from the surroundings, and that would be a negative W. Okay? So if the gas expands, W is positive based on our sign convention. And if the gas contracts, is compressed, then W is negative. The work of expansion is given by the formula work is equal to the integral from the starting volume to the ending volume of P d volume, pressure d volume. And this will always hold. And so notice that the work of expansion is positive if the gas expands. Jesus.
Oh, probably possible. Just to pick that up, yeah. When lecture videos and lecture video class are very older.
Yeah, I haven't had one work yet. That's the problem. But I'm hoping to get that fixed. But so far today, it's not. Well, we'll see. Okay, so the work of expansion is 0 if the volume is constant. And the work of expansion is negative if the gas contracts. If the volume gets smaller. You can just see that from the form of this integral, all of these things. Pressure is always positive. You can't have a negative pressure. That pressure, so in the assignment I gave you last time, you had to do that thing with gauge pressure. But in all of these kind of calculations, in all the formulas, we're talking about absolute pressure. Remember the gauge pressure thing in the assignment that I wrote in the assignment? So in gauge pressure, you can have negative pressure. You know, you can evacuate a chamber, and then the pressure inside the chamber is negative compared to 0 at atmospheric pressure. But in absolute pressure, you could have 0 pressure if there are no molecules of gas inside there, but you can't ever be negative. So this pressure is always 0 or positive, you know. And so you can just see what happens if it expands. You're integrating a positive thing from a smaller volume to a bigger volume, and so on. Like you can just look at that formula and see the way that works. Okay, so you're not super used to taking integrals with your independent variable being volume. When can you calculate this integral? When can you compute this integral? In general, the answer is you need to have P, pressure, expressed as a function of volume. Okay? The easiest case is when the pressure is constant. So now this seems like an okay time to talk about how you, like we're going to throughout this class do calculations where the pressure is held constant, the volume is held constant, temperature is held constant. Later on we'll get like no heat transfer and stuff like that. So let's think about how those things happen physically, you know. Mathematically, like, yeah, okay, so yeah, let's say the temperature is constant. But like how would you really set something up to make that happen, you know? So like to experimentally, bless you, hold variables constant. The easiest one is holding volume constant. You just use a fixed tank. This is for, these are all, well, this one is for a gas. So you would just do the thing in a fixed tank size. Okay. So any gas that you use is going to expand to fill it, any tank that it's in. So if you have a fixed volume for the tank, it's holding your volume constant. To hold pressure constant, imagine having your gas in a cylinder and apply a constant external pressure to the piston. A constant external force to the piston, I mean. One example of that would just be using the weight of the piston. So like for example, if this is your cylinder and this is your gas, the weight of the piston is the constant force. So that gas, depending on what happens to it, can expand or contract. But the whole time, the pressure that it's fighting against comes from the atmospheric pressure and the weight of that piston, and those will be constant even as that piston is going up and down. Okay. And then the last one is to hold temperature constant. Have the system in thermal contact with a large reservoir at a known temperature. So, think about these cases when like what would be an example of that? I mean, you could think of it again as a piston and cylinder. Think about having like a copper, some kind of, the piston is made out of a material that transmits temperature easily, and you do your experiment slowly enough that that heat can transfer back and forth as the temperature in the gas starts to raise or lower. And then the last thing, this isn't really constant, but we will see this from time to time, cases where the pressure is equal to some constant times the volume to some exponent, or it can also be expressed as P times V to the something is equal to a constant. These are just different ways of writing the same relationship. But what's going on in cases like these? Remember that these are just representing experimental findings for one specific type of process. So like you've set up this process and you've measured these things and you know what to expect with these. For a specific process. Okay, well, let's do some example problems. Just get used to using the work of expansion formula and using the first law. So first, let's say that the pressure is constant at 1.30 times 10 to the fifth pascals. How do you hold the pressure constant?
The cylinder is able to move, the piston's able to move, and the weight of the piston's holding down.
Yeah, right. The weight or any other force, as long like if you have something else applying 5,000 newtons of force, that's fine too. Weight is one way you can do it. And 1.3 times 10 to the fifth pascals, is that higher or lower than atmospheric pressure?
Higher.
A little bit higher. Yeah, 1.01 is atmospheric pressure, standard atmospheric pressure. Okay, so let's say that the volume starts at 0.35 cubic meters. Then the temperature is reduced in the gas, in the system, and the volume as a result. If the temperature in the gas is reduced, is the gas going to contract? Is the volume going to increase or decrease? Decrease, yep. And so the volume is decreased to 0.20 meters cubed. What's the work of expansion for the gas? Okay, so the formula says that the work of expansion is equal to the integral from volume, the starting volume to the ending volume of the pressure times dV. This is the easiest case because we have constant pressure. So this is just going to be the integral from 0.2 to 0.35. Nope, I did it backwards. The starting to the ending. So 0.35 to 0.2 of 1.3 times 10 to the fifth dV. So take that integral and you get 1.3 times 10 to the fifth V, evaluated from 0.35 to 0.2. And you get a value of negative 19,500 joules. If everything you do is in SI units, this is going to come out in SI units. That's what I'm going to tend to do in this class. Okay, does it make sense that we got a negative answer? Yeah, because the volume decreased. That's always a negative work of expansion. Any questions about that process? Okay, so how about this one? So let's say that we know that during this process, PV to the power of 1.2 is going to be equal to a constant. At state 1, the starting state, let's say that the pressure is equal to 3 bar. 1 bar is 1 times 10 to the fifth pascals, so this is 3 times 10 to the fifth pascals. And at that state, the volume is 0.1 cubic meters. And then at state 2, the ending state, we don't know what the pressure is, but we know that the volume is equal to 0.2 cubic meters. What's the work of expansion? Okay, so first of all, can we tell whether this is going to give us a positive or negative work of expansion? Yeah, what's it going to be?
It's going to be a positive.
It's going to be positive because the volume increases. All right, well, so we know that P times V to the 1.2 is equal to some constant. I'll call it C. We don't know what C is yet. How can we figure that out from what we're given?
From state 1.
From state 1, exactly. So state 1 says that 3 times 10 to the 5th times 0.1 to the 1.2 is equal to C. Okay, so did I do this one? All right, so how are we going to solve this for C? Once we find C, then we know we know that we can use this in the integral for work of expansion. Well, this is a pretty easy case. Like all we have to do is just calculate that number. So C is equal to 18,928.7. And so now we know that pressure times volume to the 1.2 is equal to 18,928.7. Well, in order to use our formula for the work of expansion, what we need is pressure given as a function of volume. So now we can multiply both sides of this equation by V to the negative 1.2, and you get that pressure is equal to 18,928.7 times volume to the negative 1.2. You with me on that? Now we have our function, and so the work of expansion is just going to be equal to the integral from our starting volume to our ending volume, so from point 1 to point 2 of pressure times volume to the negative 1.2 dV. You can pull out that constant, so this is just equal to 18,928.7 times the integral from point 1 to point 2 of V to the negative 1.2 dV. And so this is equal to 18,928.7 times V to the positive, negative 0.2 over negative 0.2. So that makes this whole thing negative. Evaluated from 0.1 to 0.2. And if you do that evaluation, you get, because this exponent is negative, you end up with positive 19,417.4 joules, which is a positive work that goes along with the expansion of the gas like we knew from the start. Okay, so practically speaking, you're going to have to deal with these like exponent rules quite a bit on this kind of stuff. Okay, so let's say now let's do another one like this. Let's see. So let's say wish I had them written out. So let's say that there's a process where we know that pressure is equal to some constant times V to some exponent, and 200 joules of heat is added. And let's say that it goes from a pressure of 2 bar, which means 2.0 times 10 to the 5th pascals, and a volume of 0.3 cubic meters. And it goes to a second state where the pressure is 0.5 bar, and the volume is 1.5 cubic meters. Let's say that there's no change in kinetic or potential energy what's the change in internal energy of the gas? Okay, so let's think through how this is going to go, and then step by step, I'm going to give you time to work on these and see if you can get through them. In the last example, this exponent relationship between pressure and volume, we knew the exponent from the start. We just didn't know what the constant of proportionality was. This time there are two things we don't know. What's different about this problem setup that's going to allow us to calculate both of those two versus just the one in the last example? There's one extra bit of information that we have here that we didn't in the last one. That's going to. That's right, exactly. In that first example, we had, is this it? No, this one. In that first one, we had the pressure and volume at state 1, but only the volume at state 2. In this example, we have the pressure and volume at state 1 and the pressure and volume at state 2. So the first step is going to be to find that relationship, to calculate A and B. Okay? After we do that, we can calculate the work of expansion. Okay? So, and after we calculate the work of expansion, we have everything we need to plug this into the first law of thermodynamics and find that internal energy. Okay? So, step one, use states 1 and 2 to calculate pressure as a function of volume. Okay, take a few minutes and see if you can work through that. It won't be so bad, but let me just go through this first step. Okay, so we have that pressure is equal to A times volume to the B. So A you can think of as let's see. So A you can think of as pressure over V to the B. And now we can plug in these two states. So the first state, A is equal to 2 times 10 to the 5th divided by 0.3 to the B. So this is from state 1. And then at state 2, we have that A is equal to 0.5 times 10 to the 5th divided by 1.5 to the B. And these two things are equal, so we can set 0.5 times 10 to the 5 over 1.5 to the B equal to 2 times 10 to the 5 over 0.3 to the B. Okay, so now we're starting to get somewhere. You can divide both sides by 1 times 10 to the 5th. So now 0.5 over 2, we have 0.25 on the left side is equal to 1.5 to the B over 0.3 to the B. And we can write this as 0.25 is equal to 1.5 over 0.3 all to the power of B. And so 0.25 is equal to 1.5 divided by 0.3 is 5. Now you can take the natural log of both sides. And remember, the thing about natural log is the natural log of 5 to the B is equal to B times the natural log of 5. So B is equal to natural log of 0.25 divided by the natural log of 5. And you get a value of negative 0.861. Okay. You'll see problems where you have to go through that set of steps, but it's always the same, you know. And then once you have that, well, we already have two formulas for A once we know what B is. So that lets you calculate that A is equal to, in this case, 70,930. And so pressure then is equal to 70,930 times volume to the negative 0.861. Okay, that step is out of the way. The next ones are mathematically much simpler. So now take this and calculate, you know, the second step is to calculate the work of expansion by computing that integral. So take a couple minutes and do that. And ask yourself, do you expect this answer to be positive or negative, first of all? That you can just get from looking at the volumes at the start. The volume's increasing, so this gas is expanding, and so we expect our integral to come out positive. Okay? Okay. So the work of expansion is the integral of P dV. So I can write this as, I can pull out the 70,930 outside of the integral. And we're going from volume 1 to volume 2, so 0.3 to 1.5. All these are in SI units, remember. Times volume to the power of negative 0.861 dV. And so this is equal to 70,930 times volume to the power of positive 0.139 divided by 0.139, evaluated from a volume of 0.3 meters cubed to 1.5 meters cubed. And if you evaluate that, you get 108,181 joules. Did anybody get that? Good.
A little bit off, but I kept the
Okay.
0.23.
Okay. Yeah, right. Great. Okay, and then the final step. Why don't I just do this just because of time? But so step 3. Now we're trying to figure out the internal energy change. We're going to use the fact that, so this is the first law of Thermo, says the change in the total energy is equal to the heat added to the gas minus the work done by the gas. Our total energy of our system is the kinetic plus the potential plus the internal energy. And the problem said that we're going to ignore the changes in these, so we don't have to think about those at all. The other thing that it said in the setup to the problem is that 200 joules of heat is added. Okay? So you have to think 200 joules of heat is added. Is that a positive Q or a negative Q? It's positive, yep. So, we have that the change in internal energy is equal to 200 minus 108,181. And so the change in internal energy is negative 107,981 joules. Okay? And that's how much the molecular motion of the gas, decreased energy-wise due to these changes that happen. Any questions about that? Okay, that's it for today. So I'll give you some first law problems and some problems that use that work of expansion integral.